Hello to everyone attending UBMOS 2024 in Macau or remotely. My name is Azeema Yaseen and I am going to be the presenter for this presentation. In the presentation today, I'm going to present about introducing Kuramoto-based temporalities in banking interaction. This is an outcome of group research work including Sutirtha Chakraborty, Damian Keller, myself, and Timoney. The work is related to a project that we have been working on for a while now, and it's called Dynamic Drum Collective. Starting with the introduction, I'll be defining musical temporalities in the research context that we have, and then about the project itself. It features interface that we used to conduct the experiment based on Dynamic Drum Collective, and then there's a section about results and findings that we got from the experiment we conducted, and finally some discussion and conclusion about the results. As we know that managing timing is critical in musical interactions and particularly in ubiquitous music ecologies. So traditional methods of synchronization that we have, they are effective for simple timing tasks, but they do not address the flexibility required in modern dynamic settings. So our goal is to explore adaptive strategies through the Kuramoto model to handle flexible temporalities within banking interactions. The traditional approaches that we have to deal with timing in musical interactions, they try to minimize delay and jitter and basically achieve the precision. And that's the most desirable thing for musical performances or interactions in casual or formal settings. However, the UBMS approach introduces time as a creative factor rather than taking it as a challenge or negatively impacting the musical interaction. To address quasi-synchronous behaviors, we need flexible frameworks like Kuramoto model, which supports adaptive synchronizations depending on maybe the skill level of the person or depending on the environment that we have to be involved in the musical interaction, and across other different timing contexts as well. From the perspective of time management, there are certain challenges that come with traditional approaches, such as hierarchical timing models, often limited the musical creativity or can influence how people involved in a creative context. In quasi-synchronous frameworks, there is more variability because the timing is flexible and there is much more space for the participants to be creative and create something regardless of the perfect timing. And that's one of the reasons, I guess, that creative projects require much more heterogeneous systems that work with temporalities that are flexible for synchronized and synchronized rhythms, and they are much more tolerant to cope with both situations. For example, if the user have enough skills to work with the timing, that is perfectly fine, but if it doesn't, it should not entirely impact the musical creativity, because there are certain aspects that users can still do and be the part of something that is very subjective but still engaging and creative to the person who is getting involved in the activity. The new iteration of Dynamic Drum Collective, we are calling version 2, incorporates a Kuramoto-based scheduling strategy. It's a model that is mostly used in complex systems to achieve synchronization. The Kuramoto model works through oscillatory interactions. In our context or the context of musical activity interaction, each participant's rhythm is treated as an independent oscillator, and every oscillator has its own natural space. So over the time, these oscillators try to adjust their timing based on the others involved in the interaction, gradually trying to reach the phases that makes a rhythm cohesive. These approaches enable adaptive timing, where each participant's rhythm can naturally align, maybe slowly, but gradually evolving towards cohesion, and maybe not the perfect timing, but still achieving a rhythm that is more flexible and grows naturally with the variations of timing. So these kind of models can be useful for flexible timing interactions or distributed interactions in real-time musical collaborations. For the system architecture, there are three main modules: input module, processing, and for output. So the input module includes timing cues and gesture recognition through the camera tracking. And following the UBMS ecologies, we use the built-in laptop or computer cameras as ubiquitous resources. So the processing module involves temporal analysis and a Kuramoto-based algorithm for synchronization purpose. And then the output module provides tempo displays and optimized audio output, ensuring the cohesive interactions during the activity. The input module of the system provides timing cues. These are visual and auditory signals for the participants, and they help them to maintain the rhythm. The cues adapt based on the participant responses, and the gesture recognition meanwhile detects both large and subtle movements. And they try to keep the experience a bit more responsive and synchronized. The second module, that is processing module, is responsible to predict user movement. So the system is designed in a way that user do not need to stand in front of the camera in a fixed position, so they can move around while they are trying to interact with the system. And to make good use out of it, it uses machine learning to adjust responsiveness. The Kuramoto-based synchronization manages rhythmic sequences, allowing participants to stay in time despite latency or spatial separation, and so responding a fluid and cohesive rhythmic experience during the whole interaction. The real-time tempo feedback is supported through output module. It helps users to adjust manually if it is needed, basically. So especially for the participants who are not skilled musicians and they need some guidance or help to stay in the timing or to create the rhythm with respect to timing. And for audio output optimization, it ensures low latency, facilitating smooth tempo transitions and improving the overall musical experience for the participants. The interface of dynamic drum collective was supported through visual feedback, so the users were able to see themselves in the camera and they were trying to position themselves and their gestures relative to the objects on screen. Of course, they were trying to make the gestures as close to as the drumming gestures, but they were understanding that how capable the system is to match the speed of the movement and the scale of the movement. And there was also an option to support the calibration. For example, if we look at this interface picture, these are the boundaries or the objects to support different sounds in the interface. So there was an option for the users to position them on the screen depending on the preference that they want to have for the environment they're going to use for the musical activity and for synchronization. So this is a screenshot of Dynamic Drum Collective. You can see as a user standing in front of the camera, and these are different colors, and every color that you're seeing here is representing a percussive sound. The blue dots that we can see here, they were designed to help user to understand their position in the space and relative to the objects on screen, because otherwise it was hard. In the previous version, we observed that it was hard for them to understand where exactly they're moving and how close they have to move to trigger a certain sound. This interface is a bit simple, yet meaningful, because from a non-musician perspective, we didn't want to make it more complex, so they are trying to think more about the interface and objects on the screen rather than thinking about creating something musical or create a rhythm. The experiment was conducted with 2 participants. One of them was a professional drummer and the second participant was a non-musician. Each participant was asked to iterate the interaction twice with the system, and there were 2 sessions for each participant. So for the first session, it was over 10 minutes of exploration to explore the system and to understand that how the sound works and what kind of gestures they can perform to interact with the system and to trigger the sounds. And the second session was the main part of the experiment to allow the participant to synchronize at various tempi, ranging from 60 to 130 BPM. Here is the illustration for the experimental setup and the sequence of the process. So it starts with metronome cues for the participants, helping them maintain a consistent beat. And this metronome signal is directed to the drummer as a reference for synchronization. Drummer here is representing the participant, and we had 2 participant, musician and the non-musician. The drummer's movements are captured by a camera sensor then, and this sensor tracks the gestures and positions which are then processed in real time. The next to that is we have gesture-based drum module. The camera input is fed into a gesture-based drum system, which interprets the drummer's actions, gestures as drumming gestures. Basically, these are actions, and this module understand them as gestures and map those actions to gestures. And then those gestures are considered as drumming gestures before the sound is triggered. So this module translates physical movements into virtual drum hits or beats. Then audio output. The generated drum sounds are sent to an audio output system, providing feedback to the participant and enhancing the interactive experience. So they were able to hear back what they were trying to play. So they have a feedback, and if they were trying to improve it, they could just change it in the next iteration to learn from it and to get the desired outcome as they want to. So next to that is Kuramoto synchronization module. This module applies the Kuramoto synchronization algorithm, that is the main part of the work here, to take the input from this part, the audio output, and then Kuramoto synchronization algorithm comes here to align the audio output with the target tempo. It adjusts the timing of the audio output to match the intended rhythmic structure that is required, accommodating for any timing variations in the drummer's performance. And the final part is tempo output. Finally, the tempo output helps in maintaining a cohesive rhythm throughout the interaction. So ensuring that the audio output remains consistent and aligned with the metronome cues, because that's what we are trying to achieve here. That's how we were looking forward to, that how this tempo is achieved by a musician, considering the timing and the variations over the whole activity, and also for the non-musicians. So following this process, the participants were trying to synchronize their movements with the metronome track, and we asked each of them to do 3 dials at each tempo setting, starting from 60 and until 130 BPM. Now let's look at some findings and results that we observed from the experiment. So in the experiment, we recorded the synchronization data across tempi from 60 to 130 BPM. A musician from this value, for example, 5.45 seconds to synchronize 70 BPM. It was better for the musicians to synchronize at the mid-range tempo, which was 3.71 seconds and 90 BPM, as compared to 5.4 at 70 BPM. So the better performance was for this range for 80 to 100 BPM, particularly for 90 BPM. And for example, for the higher tempos from 110 and plus, it was hard for the musician to synchronize at higher tempos. Larger gestures required by the system posed a challenge, especially when the drummer used smaller movements. So of course they were trying to make the biggest gestures to trigger the sounds. It was the time plus the time from the system to detect the gesture itself. So there was a bit of delay and latency caused by the system that made it challenging for the musicians to achieve the tempo at the desired speed or the desired skills that they have. So here we are presenting the data, the recorded data for the 3 trials that we did with the drummer for the BPM from 60 to 130. So the drummer achieved the best synchronization times at mid-range tempos from 80 to 100, especially at 90 BPM. Here it is, which is 3.71 at trial 3, where they synchronize in as little as 3.71 seconds. So this suggests that the system was most effective at these tempos for the drummer, allowing them to quickly align with the metronome. So then we have the slower tempos from 60 to 70 BPM. At slower tempos, synchronization times were longer. If you look at the trials, starting from a very high value, 10.2, coming towards 5.74, but they are still higher than the minimum value that we got for the mid-ranges. So for the higher tempos, 110 to 130, it was because system required larger movement, and that conflicted with the skill of the drummer and how they wanted to achieve the tempo. So it's more about the system limitations than about the participant, how they were trying to achieve the tempo. So maybe there is much more capacity with the system to improve, to achieved much more accuracy to detect gestures and allow for much precise movements during these kind of instructions. For lay participant session, there is much more variability that how they were achieving the tempos. And based on the data that we have, the non-musician synchronization was more diverse than the musicians. While slower tempos posed challenges, the participants showed improvement in mid-range tempos, achieving optimal synchronization between 80 and 100 BPM. Higher tempos were again challenging to maintain. So for example, here at a slower BPM, larger delays, 12 to 17 seconds, and then in mid-range it was as low as 2.7 seconds at 90 bpm, which is surprising because for the musician it took more time to synchronize, and one of the reasons was because musicians are highly skilled. The musician was highly skilled, and it was hard for them to play something which was not as okay. So for the data that we got for lay participant session, so the non-musicians synchronization was more varied and there is much more diversity, while slower tempos posed challenges. For example, like here the delays were very long. So the mid-range tempos, the participant achieved optimal synchronization between 100 and 100 bpms, achieving in 2.7 seconds at 90 bpm. The interesting thing is that for the musicians it was around 3 seconds, and for the lay participant it was 2.7 seconds. So one aspect to look at this might be because the musicians, they are very skilled to understand the timing and the rhythm, and for the musician it was challenging to understand the system response and the latency issues, and it was harder for them to understand how system is trying to adapt to their gestures, and they had to perform differently because of the system's limitations. So maybe for musician it was much longer than the person who was new at this, and they were much quicker to adopt to the system response, even though the system was challenging itself. So again, for the higher tempos, 110 plus BPM, difficulty maintaining the synchronization because of the system limitations, and from that perspective, this range of tempos was much more achievable for the lay participants, even though better in the both situations, in the board session for the drummer and the lay participant, but better for the lay participant session because they were much more flexible for the idea of timing and achieving rhythm in music, and they were much more adapted to the system challenges. So this slide shows the lay participant session results from the dynamic drum collective experiments, focusing on untrained subjects' ability to synchronize across different tempos, ranging from 60 to 130 BPM, the same range that we use for the musician as well. So the bar chart illustrates synchronization's time across 3 trials for the lay participants as well, trial 1, trial 2, and trial 3. So the slower tempos, the participant took longer to synchronize at slower tempos when times reaching up to 17, almost there, 17 seconds, for some trials at 70 BPM. So slower tempos seems challenging for the untrained participants, potentially due to the difficulty in maintaining a steady rhythm without prior musical training. Or another aspect be because it was first trial and they were getting used to the idea of timing, so it took them longer time, it took the participant longer time to synchronize and understand that how they can do better in the next trial for the next range of BPM as well. So for the mid-range tempos, here again the best value is 2.7. The range is the same as we have for the musician, but of course the value is much more smaller for the non-musician. And reason that I mentioned earlier, maybe for the non-musician it was easier to scale down to the system's ability to detect the gestures and trigger the sound than the musician. For the higher tempos, around in 110 BPM, synchronizations become more difficult again with times around 8 to 11 seconds. So the participant was unable to synchronize at 120 BPM or higher, as shown by the 0 bars, indicating that these faster speeds were beyond their comfort level for maintaining the rhythm. So participant for the non-musician, because the interface was very simple. It was easy for them and they were able to enjoy it because they didn't have to think a lot about the interface, rather than thinking about what they can make, what they have on the interface. So optimal tempo range, similar to musician, was again 80 to 100 BPM. Now moving towards Kuramoto-based implementation and how we used it for the experiment, and it was implemented with the project. Let's have a quick look again at what it is and how it fits in our context. So the Kuramoto oscillatory algorithm synchronizes participants by treating each rhythm as an oscillator, having its own space, with timing adjustments that bring these rhythms into alignment. So this gradual synchronization makes it suitable for distributed interactions, in person or for real-time online musical interactions. How the synchronization was achieved through Kuramoto-based implementation. So this model uses a concept called coupling strength. And basically the coupling strength means bringing different oscillators, in our context participants' rhythmic actions, into alignment. So each oscillator starts with its own timing or phase, and the model continually adjusts the phase of each oscillator based on the timing difference with other oscillators. So this phase adjustment happens repeatedly, with each oscillator being slightly pulled towards the phases of others. Over time, gradually, these small adjustments help reduce the timing difference between oscillators, gradually bringing all oscillators into synchronization or phase alignment. And to test the results for the Kuramoto-based implementation, we conducted experiments across a range of tempos from 60 to 130 BPM, similar to musician and non-musician. So for each trial, we measured the mean synchronization time, which is the time it took for all oscillators, participants' rhythmic input, that's what I mean here, to align. So let's look at the results here, that how it turned out with the Kuramoto-based implementation. Here we are presenting the results from testing the Kuramoto algorithm for synchronization across various tempos from 60 to 130 BPM. And the chart shows that the synchronization times in seconds for 3 trials at each tempo, as we did for the other 2 participants. So the key observation that we can extract from this data is that as the tempo increases from 60 to 100 BPM, the time taken to achieve synchronization decreases. For example, at 60 here, so the time that we have is 6.8 seconds, while at 90 BPM it drops to around 3.3. That is a minimum value here. So this trend indicates that the algorithm synchronizes faster as the tempo increases from this point to this point for this range, and showing its efficiency in aligning rhythms at moderate speeds. Moving towards the highest tempos, starting from 110 and the onwards. So at tempos above 100 BPM, the synchronization time, that's what we call plateau. So we are achieving that. So it stabilizes around 3.7 seconds, and that it stays around the same value. So this plateau suggests that the algorithm reaches its limit in improving synchronization time beyond a certain speed. It could be due to computational constraints or the natural limit of how quickly oscillators can adjust at very high speeds. So one thing that we can observe from here is the consistency across trials, especially to the trials, these ones and these ones, the last ones. So the algorithm shows consistent performance across the 3 trials at each tempo, not much variations, with only slight variations though in synchronization time. So this consistency indicates that the Kuramoto model provides reliable synchronization, making it suitable for scenarios requiring stable rhythmic alignment. So here we have the combined synchronization results by comparing synchronization times across different tempos, 60 to 130 BPM, for 3 participants, a drummer, a non-musician, and the Kuramoto algorithm. So each line represents the synchronization performance of these 3 groups, providing some information and some observation that we can get from the experiment data. For the drummer, the first participant here, we can see that they show consistent and relatively low synchronization times across all tempos, with a slight decrease in time as the tempo increased from this point to this point, as 80 to 100. So the drummer performed well at both moderate and high tempos, relevant to slower ones. However, synchronization times slightly increased again at the highest tempos, around 130 bpm here, indicating some challenges. And in the previous slides, I did mention that these challenges were also because system was not capable of understanding and translating the very quick and very small movements and gestures for the musicians. So for the non-musician, from the non-musician perspective here, the non-musician participant exhibited longer synchronization times in the beginning because they were learning about it, and it was their first experience with the concept of timing to achieve the rhythm and in musical interaction. And then when the interaction evolves, the time gets lower from this point, 80 to 100, similar to musician, but the value is much lower here for the non-musician as compared to the musicians. So however, at tempos above 100 BPM, synchronization times increased again, showing that the non-musician here, for example, at this level, found it difficult to maintain rhythm at higher speeds. And after this level, they were not even trying to achieve it because they were not able to do it. And for the third group, Kuramoto algorithm, so for its synchronization time, it achieved the fastest and most consistent synchronization times across all the tempos, generally below 6. For example, after this value, we can see all the values here are 6, except for the highest tempo until it becomes plateau, and then it didn't go beyond that value higher or the lower after 110 bpm. So the algorithm's performance was stable across all tempo ranges, highlighting its effectiveness in achieving synchronization without the natural variability seen in human participants. So unlike the drummer and non-musician, the algorithm maintained near constant synchronization time even at high tempos. And finally, from the experiment data and the presentation, there are certain points that we can conclude. For example, for the first point, the dynamic drum collective version 2 shows potential for flexible synchronization in ubiquitous music context, adaptable across skill levels. And I think this is one of the things that we're trying to achieve to make the creativity related activities involving music much more affordable and available to the people with different and varied level of skills. And some limitations are there, but they are more technical, and how the system behaves to the person's own capacity to deal with the timing and the music and audio-based instances. So if we have the system, they are much more efficient to detect the gestures precisely, more accurately, and with the lower latency level. Maybe there are much more opportunity and availability of possibilities for similar kind of interactions. But from the Kuramoto model perspective, it holds promise for handling temporal variability, especially because it's very constant and consistent. So we can further explore that how it can be used to design the systems that have more affordability for the people to engage in musical activities with different level of skills. Finally, for the last slide of the presentation, I would like to mention some key takeaways that we have from the experiment and that we learned ourselves from the project, that there is need for systems that accommodate both large and small gestures and incorporate multimodal cues. And the multimodality of cues is very important because it is going to help the person with its ability to deal with the timing in similar activities. So the person is much or more skilled, then maybe they are not much more lean towards the visual cues, but they mostly rely on the auditory cues. But for the person like a non-musician or somebody who is looking forward to visual cues and some feedback before they improve their auditory skills, it's important to incorporate those things into the system design as well. And adaptive algorithms like Kuramoto's offer an effective way to address human variability and challenging tempos. It can provide a direction for future improvements and to see that if there is possibility to design system with both synchronized and unsynchronized events, then how far we can go in sense of creativity and to utilize those systems in real-time environments. Here are some references that we have cited in the presentation. Two of them are related to the project that we have been working on. And thank you so much for your attention, listening to the presentation. And if you have any question about the project, presentation, or the project functionalities, me and my group members would be happy to answer that. Thank you so much.